Good afternoon, all the participants, and our today's resource person, Honorable Dr. Sharan Kumar Goudar sir, to the second session of day third of our AICT IST sponsored online induction refresher program on innovations in concrete technology. I would like to introduce our today's resource person, Honorable Dr. Sharan Kumar sir. Dr. Sharan Kumar Goudar sir has done his PhD on determination of engineering properties of steel concrete interface of reinforced concrete exposed to marine environment from National Institute of Technology, Karnataka, Surathkal, Mangalore. He is currently working as Assistant Professor in Civil Engineering Department, College of Engineering, Pune, Maharashtra from September 2019 to till date. He has also worked as research scholar at National Institute of Technology, Karnataka, Surathkal, Mangalore from July 2015 to September 2019. He worked as an assistant professor in Civil Engineering Department, Mangalore Institute of Technology and Engineering, Mudbidri, Dakshin Kannada from July 2014 to June 2015. He worked as an assistant professor in Civil Engineering Department, Vivekananda College of Engineering and Technology, Puttur, Dakshin Kannada from July 2013 to June 2014. He has published many articles in international journals and done extensive research on microstructure studies on steel concrete interface, corrosion studies on reinforced concrete, durability studies on concrete in aggressive environments, sustainable concrete, production of ultra high performance concrete, and many more. Let us begin our today's session on reactive powder concrete production and microstructural investigation by Dr. Sharan Goudar sir. I would like to request sir to start the session.
Hello, ma'am.
Yes,
Thank you
sir.
for your overwhelming introduction.
Yes, sir.
If you could stop the sharing, then I would like to share my screen.
Yes, sir.
Okay. Good afternoon, everyone. Hope I'm audible and clear.
Yes, sir.
Okay. So today's topic is a reactive powder concrete production and microstructure investigation. So this is the topic which is very close to my heart, as I pursued my master's in on this topic, that is reactive powder concrete, and also some of my work continued in PhD. But later on, I've changed my topic to steel concrete interface, as mentioned by Madam. So before we move further, let me tell you what is this reactive powder concrete is. Okay, so before I move further, I would like to show one small video so that you'll be able to understand what I'm talking about, what kind of concrete that I'm talking about. If you see, this is the equipment that we have used in NIT Surathkal. It's already there. This is the kind of concrete that I'm talking about. If you observe, there is no coarse aggregates. It's very fine powdery material. And what are its composition and all, we'll speak in a little bit. If you observe here, the slump or the flow value of this concrete is very high. Okay, so this is the concrete that I'm talking about. Hope you can understand. So that is what the reactive powder concrete is. Before I move on to the production and the microstructure investigation, let me introduce the topic first: reactive powder concrete. Okay, so we'll divide that into three parts. The first is a reactive part, and powder part, and concrete part. So I'll focus on the middle part first, that is powder concrete. What do I mean by powder? All the materials which I have used in this concrete are in the form of very fine materials. So that's why we call them as powder. And as you saw in that video, there were no coarse aggregate at all. We have completely eliminated the coarse aggregate while producing reactive powder concrete. Okay, so that is the meaning of powder, because most of the material are in the form of powder. Let me move on to this first term, reactive. Why do we call this as a reactive? As I'm removing the coarse aggregate, obviously I have to fill that void or fill that coarse aggregate gap by some other materials. So those materials are silica fume, quartz powder, and very fine silica sand. What do I mean by silica sand? Silica sand is in the range of 600 micron to 300 micron. We don't even go for 4.775 mm aggregates, that is fine aggregates. We use very fine material, which are the highest size of the material that we have used was 600 microns while producing this concrete. And the materials, silica fume, and we use a lot of amount of cement. So that's why all the materials are very reactive. You can get very high early strength. Because of that reason, we call this material as reactive powder concrete. Okay, so why do we call this reactive? We'll come that in a minute or so. So this is the contents that I'll run through in today's presentation. I'll be talking about what is reactive powder concrete, and I'll briefly introduce the concept to you. If not all, I'll try my best to introduce the concept to you at all. So next, we'll study some of the applications, practical applications, which are implemented worldwide. Then we'll focus on production of reactive powder concrete, because there are no standard codes available yet. In the entire world, there are no standards available to produce reactive powder concrete. Every country is following their own standards. So we have tried our best to produce one simple way of producing reactive powder concrete. So after discussing this, we'll go for microstructure investigation. So what are the different ways? There are different steps, right? Which material I have to use, and how much time I have to rotate the blades, how much quantity I have to add, what is the plasticizer content, how much silica fume I have to add. All these are part of production. So what are their effect on microstructure? That we will discuss with the help of SEM and EDS analysis. So today's presentation will be only about this. We will talk about the production of reactive powder concrete and some microstructure investigation that we have done in our labs. As you already know, reactive powder concrete is classified as ultra high performance concrete. It comes under ultra high performance concrete. So we have basically the grade of concrete, normal strength, or we call them as 30 to 60 MPa concrete, normal strength concrete. Then comes the high strength concrete from 60 to 100 MPa. Those are high strength concrete. And above 100 MPa to 150 MPa, those comes under ultra high performance concrete. So what are the difference between high performance concrete, ultra high performance concrete? We'll see in coming next few slides. Okay, the concept of this reactive powder concrete is originally developed in 1990s in France. So reactive powder concrete, as you already know, it's very cohesive material and very fine powder materials we are using. That's why there are no voids at all inside the concrete. If you see the coarse aggregates, we have a lot of interfacial transition zones in our concrete. Those interfacial transition zones of coarse aggregate will be avoided here. And to make that material little ductile, reactive powder concrete is very brittle material. If you see or if you test reactive powder concrete, when it fails, it makes a blasting sound, right? So bomb, I hope everybody visualize. So likewise, the reactive powder concrete cubes will blast. So to avoid that part, we use fibers. Okay, so this is reactive powder concrete is a fiber reinforced reactive powder concrete. So also we use silica fume, and we use very low water cement ratio in the range of 0.18 to 0.22. The maximum water cement ratio that you can use in producing reactive powder concrete is 0.24. Even the code suggests in France or in Chinese people, they suggest that maximum water cement ratio you can use is 0.24. For normal concrete, what we use 0.45 to 0.55. But for producing reactive powder concrete, we use very low water cement ratio, that is one of the advantage that we have. Okay, then the flow value that we get it from the powdery material as well as superplasticizers. Okay, so also elimination of, there are four reasons why we get very high strength concrete. Reactive powder concrete is usually comes in the range of 150 to 800 MPa strength concrete. Normal concrete we usually get in 100 to 200 MPa, but reactive powder concrete ranges from 200 to 800 MPa strength concrete. In our work, we could able to produce around 190 MPa strength concrete. Okay, still we are working on this material, so we are trying to achieve at least 250 MPa strength. Okay, so what are the reasons for that? We have eliminated the coarse aggregate, and we have used very low water cement ratio, application of superplasticizer, addition of fine steel fibers. We also used heat curing. Heat curing is mandatory because if you want to achieve very high early strength, we have to go for heat curing here. So also if you have the facility, then you can even apply the pressure also, that is autoclave curing. If you do that, then you can even achieve very high early strength. If you see, these are the materials that we use to produce reactive powder concrete. The first one is cement, silica fume, quartz powder. This is one important material. In the place of coarse aggregate, we are trying to replace with quartz powder. What is the proportion and all, we'll see in the coming slide. Then we use silica sand. Then we use superplasticizers. Okay, so these are the standard codes, specific gravity of the materials, types and all. If you want, I can share the PPT with you guys, so you can visualize at any point of time later after the presentation. So RPC mixed proportion. The major part of this reactive powder concrete is sand, this much proportion, and cement. So this proportion varies from what kind of mixed design that you are going to do. Okay, so that's why I've not represented in any terms of percentages here, because it varies from person to person. What do you want? That varies. Usually I could say one thing, in my studies, I have used a cement content of 900 kg per meter cube. Yes, you heard it right. We have used cement content of 900 kg per meter cube to produce reactive powder concrete. We have also used silica fume. We have used quartz powder, water and superplasticizers, and fiber. These are the fiber content: water and superplasticizer, quartz powder, silica fume, cement, and this is major portion is sand. So we have completely avoided coarse aggregate in producing reactive powder concrete. If you see high performance concrete and reactive powder concrete is a ultra high performance concrete. Okay, UHPC we call. What are the typical some of the mechanical properties I've listed here? Compressive strength for high performance concrete, it ranges from 60 to 100. There is one major issue we usually send. What is the difference between high strength concrete and high performance concrete? Okay, high strength concrete is very much good in taking the compressive strength. It ranges, the compressive strength ranges from 60 to 100 MPa. If you come to high performance concrete, along with high strength, high performance concrete are very much durable. If you apply them in any harsh conditions, their performance is significantly higher than high strength concrete. So that is comes under high performance concrete, and reactive powder concrete is a ultra high performance concrete because of these three reasons. One is, see the compressive strength, it ranges from 200 to 800 MPa. If you come with the flexural strength, for high performance it is 6 to 10 MPa. For reactive powder concrete it is 40 to 50 MPa. Young's modulus is also very high for this. And fracture energy. What do you mean by fracture energy? So once, imagine your concrete starts cracking because of high loading. Your high performance concrete can take up to 140 joules per meter square of energy. But if you see the reactive powder concrete, it takes around 1200 to 40,000 joules per meter square of energy. What do you mean by that? As we are adding fibers here, the failure rate or tensile strength or flexural strength will be very high. Because of that, the fracture energy, the load carrying capacity after even the cracks appear is very high for reactive powder concrete. So as you can see, the high strength of reactive powder concrete is due to high cement content, very low water cement ratio, high reactive silica fume, proper agglomeration adjustment of fillers, incorporation of steel fibers, and curing under hot regimes. Why we have to cure under hot regimes, we'll come to that in a bit. That is very, very important for producing reactive powder concrete if you want to achieve high early strength. It's because of this hot curing regime. As you might be wondering, the cost of this reactive powder concrete will be at least 3 times of high performance concrete. So if your high performance concrete production cost is nearly 4,000 to 5,000 kg per for 1 meter cube of concrete, outside they may charge you around 4,000 to 5,000 rupees. For reactive powder concrete, it may vary from 15 to 20,000 depending upon the need of your construction. Okay, so it is at least 3 times costlier than our normal concrete or high performance concrete. Why it is costly? Because we are using high amount of powdery material, especially high amount of cement and reactive silica fume. Silica fume is a very costly material. What is the advantage? Then why people are going for this very costly material? If you see some of the applications wherein you may not worry about the cost of concrete, you want high performance, and reactive powder concrete is a ultra high performance concrete. So in very specific applications we use reactive powder concrete. So what are the applications? We'll come to see them in a bit. Okay, so world's first reactive powder concrete structure is a precast pre-stressed pedestrian bridge in Canada in July 1997. Even though it has been started in 1997, the earlier in 1990s only in France, people have started working on this. But this is in 1997. This is the first precast pre-stressed pedestrian bridge which is constructed in Canada in 1997. Also, there are a few of the railway bridges were constructed, power plants were constructed, seawall anchors, nuclear power plants, weapon factories, manhole covers, storm gates, footbridge. No, all these things are constructed. If you know, long span bridges. I have some photos also where we can use this. So long span bridges, we use high-rise buildings, blast resistant structures, cleans and chimneys, concrete barriers in highways, sewers, culverts, pressure pipes. In all these things we use. The main application of uh, reactive powder concrete comes in power plants, weapon factories, seawall anchors, and all those things. Okay, so these are a few of the practical applications. As you can see, this is one of the vehicular bridge which is in Iowa, Canada, and this is Virginia. As you can see, this is how the concrete flows. The flow rate of this concrete is around 200 to 300 mm. Few other applications. This is the pedestrian bridge in Canada. This is the first reactive powder concrete. See this and this, that is from reactive powder concrete, and these are steel hollow pipes. Okay, so the deck is of reactive powder concrete. This is one of the pedestrian bridge, first of its kind, which is constructed in 1997 in Canada. This is another vehicular bridge which is constructed in Australia. The span is 15 meters and width is 21 meters. Remember, as I said, this bridge is of they have not used any reinforcement here. Only the steel reinforcement, steel fibers they have used as reinforcement. Without reinforcement, they have constructed this vehicular bridge. That is the advantage. Because of this high tensile strength carrying capacity, we may avoid using reinforcement bars at all. So this is another pedestrian bridge. It spans around 60 meters in length. So it is in Japan, foot-over-bridge Japan. Without any passive reinforcement, they have constructed this foot-over bridge, okay, which is very long span. So application of reactive powder concrete comes under in this way. because it's very high tensile carrying capacity, and even the flexural strength of reactive powder concrete is very high. So one more bridge in New Zealand, Footdoor Bridge. So these are a few of the applications. I couldn't get the images of power plants. They said that it is copyrighted, so that's why I couldn't get the images of power plants which are constructed using reactive powder concrete. But somehow, if you get me, then please share it. Share it with me. So these are few of the applications. Then, as I'm discussing about the microstructural studies, am I audible, guys? Hello.
Yes, sir.
Okay, it is for the participants. If you have any doubts, you can stop me at any point of time, and you can ask the questions. So there should not be any monotonous, just talking and you guys listening. So please interact. If you have any doubts, then and there, switch on the mics and you can ask any questions. I would love to interact with you guys then and there. Rather than waiting for end of the session, we can have this session now itself. And also one more thing, if you put your questions in chat box, I may not be able to see them right now. So it's better you unmute yourself and please speak out. Okay, so we have seen the application of reactive powder concrete till now. As my studies focused on microstructure study, before I move on with the production, how to produce reactive powder concrete, I would like to brief a little bit on microstructural studies of concrete. What do you mean by microstructure study? Okay, so usually if you see the cameras, high-end cameras, if you click an image or while during clicking, you can zoom it, right? For 10x, 20x, 30x, 40x, 50x, even a few of the mobile cameras are there. They can zoom even up to 150x zoom. Okay, so same material, if you keep your concrete and zoom it to around 5000x or even 10,000x, 25,000x, something like that, those kinds of study, we call them as microstructural study. Okay, the images that we get, they are in terms of 10 raised to minus 6 range. That zoom will study, that kind of study we are calling it as microstructural study. Okay, so what are the ways? These are the different methods available for microstructure study. We can use even optical microscope also, but the resolution will be very small. As I'm talking about the resolution more than 500x or 200x. So these are the methods. First method is electron microscopy that we have already used. We usually call them as scanning electron microscopy, SEM we call. So there are different other electron microscopies available. One is environmental scanning electron microscopy. Another one is field emission scanning electron microscopy. What is the difference between these two? In scanning electron microscopy, you can use only the materials which do not have or which is free from any surface moisture. If you have surface moisture, then you cannot observe anything in scanning electron microscopy. That's one of the disadvantages in scanning electron microscope. And whatever the microscopes that you see around us, most of them are scanning electron microscopy. Okay, so what is environmental scanning electron microscopy? Here, even you can study the live materials. For example, roots. You can study even the algae, which are in some fluids. All of that you can study in environmental scanning electron microscope. Even you can study the cement paste, how the cement paste sets, what are the products that are forming at different hours, that you can study using environmental scanning electron microscope. Very rarely they are available and they are very costly. The next one is a field emission scanning electron microscope. In these two, while producing the electrons, they use tungsten filament. But here in field emission scanning electron microscopy, they use carbon material, some form of carbon material, because of which the resolution or the image quality that we get in field emission scanning electron microscope are very high. In field emission scanning electron microscopy, you can use the wet material as well as dry materials. I hope you can understand the difference between these three. SEM is the normal, that one that we use for hard materials. In environmental scanning electron microscope, even the paste materials also you can use, and field emission, it's one of the high resolution FEMs available. Okay, so these are electron microscopies available, and I have used scanning electron microscopy for my studies. So next one is usually whenever we come across with SEMs, it is already equipped with EDS also. What is EDS? Energy dispersive spectroscopy. So energy dispersive spectroscopy will give us the elemental composition within a selected area. For example, what kinds of elements are present in our material? In concrete, if you're talking about concrete, we'll focus more on concrete itself. The first material that we come across is silica, calcium, aluminum, magnesium, and all that. If you select a particular area, what kind of material or how much percentage of that material is available in the selected area, that can be identified using energy dispersive spectroscopy, or we can call that in some easy form EDS or EDX also. Energy dispersive X-ray spectroscopy, some of them say. So they call it as EDX, but general form is EDS, energy dispersive spectroscopy. So the second method which is available for us for microstructure study is X-ray diffraction, short form XRD. XRD, it will give you the ionic composition. What kind of ions are there in your material, that can be studied in XRD. And third one is mercury intrusion porosimetry. We call them as MIP. Mercury will pass mercury to from one end, and other end how much mercury will be collected. Based on that, we'll study the porosity inside the concrete. This is one of the vague method, mercury intrusion porosimetry, vague method we can say, but people are still using that. The fourth one is TGA, thermogravimetric analysis. Will heat the material to specific temperatures up to 1000 degrees Celsius, and at what temperature what evaporates or decomposes. Based on that, we can even tell this material was present at this temperature, and depending upon the decomposition, we will tell that that material was present. So these are four different methods available for microstructural study. In the present study, I have used scanning electron microscopy and EDS most probably. And for few samples, we have used even X-ray diffraction also. So let us discuss about the further things. So this is one scanning electron microscopy which I have used, which is available in NIT Surathkal. The company name is ZEISS, scanning electron microscopy. Coming to the specimen preparation, specimen preparation is very, very important while going for SEM studies. In most of the cases, what we do the compressive strength of the cubes, and we'll take a small chunk of that and we'll directly go for SEM observation. That is one kind of study, but usually that is not a scientific method of going for the microstructure analysis. We usually have to cut the sample using slow speed cutters. Then we have to epoxy impregnate it. Then we have to polish the material with different grades of polishing. Then we may use even diamond polishers also to get very fine surface, so that if the surface is very fine, the quality of images that we get will be very high. If the resolution is very high, then analysis can be very prompt. Okay, so sample preparation is very, very important. There are lots of papers available on sample preparation. If you say sample preparation itself can be a 1 hour topic. If you want to discuss sample preparation, it's very, very complicated sample preparation. But please note that before going for SEM analysis, sample preparation is very, very important. So this is how the samples you can keep inside the SEM chamber. There are 1, 2, 3, 4, 5, 6, 7, 8 slots are available. See here, I have kept 2 of my samples here. So at a time, you can keep 8 samples, 8, or even you can use this also, 9 samples you can use at a time. Okay, so before keeping this material, we have to apply a conductive coating. As concrete is non-conductive, we have to make the surface conductive, or else what will happen, there will be a bright image. You cannot see anything. Because of that, the images looks distorted or very bright, something like this. So because of that, we have to sputter that material with gold or palladium. This is the sputtering material that we use, and this is the sputtering machine. A thin coat of gold will be applied on the surface of the material so that the surface becomes conductive. So once it is conductive, then you can take that sample for SEM analysis. Without this, it is not at all possible for getting good quality images. So this is how the samples look like. Those two samples which I've kept, they are here, and this is the emission. You can see some small amount of X-rays are being followed here, and this is the camera or detector, and somewhere here it will be a camera. So from that we'll get the images. So this is the detector. So this is the keyboard that they use, operating board. This is for magnification and this is for focus. There are different even tools are available. Even personally, I have operated this. It's very easy to operate and very fun also. If you try, if you have ACM images in your colleges, please go and try to operate it. It's you can see. One of my friends said while going for ACM images, it is usually like going for a movie. A director knows what he wants to shoot or what the character has to say. Okay, so that's why before going for SEM, you have to be very precise what you are looking for. If you are looking for porosity, then focus on that porosity only. So focusing and magnification based on the literature, you have to finalize your magnification as well as focus also. Even the working distance is also there. So working distance is none of your concern. If you get the good kinds of focus and magnification, that's more than enough. For comparison, remember, we have to get the photos or images of same magnification. Then only we can go for even image analysis also at a later point of time. Okay. So that is that. You must know what you're looking for in an SEM image, then find out that image and get such kinds of images. So as I was talking about working distance, see here, magnification is 97x right now. This WD, that WD is 2.8 mm, this working distance. The distance between this and this is 2.8 mm, and this varies up to 9 mm. Okay, that is the working distance. So if you cannot have samples of very high thickness, that's why they usually restrict the specimen thickness to around 4 mm or 5 mm, not more than that. So this is how the images look like. Once you start getting the images look like this, and the other you can have here EDS analysis of this particular part. Okay, there are usually two kinds of SEM images that we get. One is backscattered electron images and another one is secondary electron images. Backscattered electron images are specially used for image analysis. Most of the times we get secondary electron images, but those who are really interested in image analysis and quantifying something from those SEM images, you have to go for backscattered electron images. So what are these two? We'll have a brief discussion on this. Backscattered electron images, they have very high energy. So that's why they penetrate the sample up to 5 micrometer depth. On the surface, they penetrate up to 5 micrometer and the electrons will be scattered back. Those scattered electrons will be collected and image will be produced based on that. Such kind of mechanism, we call such kind of images as backscattered electron images or BE images. The backscattered electron images looks something like this. This is the 20 kilovolt energy that we have given. Zoom is 60x. These are two different images that I'm trying to show here. This is at 60 zoom, 200 micrometers. That means this is for measurements. This measurement, that means it shows only 200 micrometer area. You see here something called BEC, backscattered electron. So this BE is backscattered electron. It shows. Somewhere around this, you can easily notify there is a black void here, right? So what are these black voids? What are these white patches and all? We'll see them in a bit. So this is how you see the backscattered electron images. Okay. Secondary electron images, the energy of electrons are very low. That's why they cannot reflect back. On the surface only, they reflect back and reflected images will be collected. So this is how you get the images. These secondary electron images are very good for the samples which are not polished. For example, once you do the compressive strength test, you can take those samples only, such kinds of samples, after sputtering and all, you can see the images. Based on this, you can see the depth, where are the voids, all that study you can do. This is only qualitative analysis. If you want to go for quantitative analysis with SEM images, then you have to go for backscattered electron images. If you see here, the magnification is 200x, the distance is 100 micrometer, and this is secondary electron images. Okay, so this is secondary electron images. Same way, I have just zoomed this part. This is 200x, and if I zoom it to 3000x, this same part looks like this. Okay, so from this we can identify this is unreacted particle. This is calcium silicate hydrate, and if in lower zooms we can see the sand grain. Okay, beside that there is calcium hydroxide, the brightest part which appears. We will come to that, which is brighter and what does indicate. We will come to see in a little bit of time. So this is how you see the secondary electron images. Even early hydration products also you can see at 1700x zoom, you see some needle-like structures. These needle-like structures are called as ettringites. Ettringites are converting into monosulfates. Monosulfates, they convert into CSH or the byproduct calcium hydroxide. Right? This is one beautiful image you can see. The same image, if I zoom it to around 4500x zoom, see here, you can see the needle-like structures here. Okay, even if you want particularly on this particular portion, on this particular portion, you can use, even you can go for higher resolution, you can go up to 25,000x. In my case, I could go up to 25,000x. If you have field emission microscopes, then you can even go for 1 lakh, 2 lakh, even 5 lakh also for higher magnification. Then what are the uses of this? If you know the microstructure, you can correlate the micro properties to macro properties. That is what I have done in my studies. I have tried to identify the micro properties of reactive powder concrete. Then I'm trying to correlate that to macro properties. The strength or high strength or low strength, whatever the strength I'm getting, I'm trying to analyze with the help of microstructure study. Okay. So this is one more secondary electron image. This is a sand particle, and this is some hydration products. If I zoom, I've just zoomed this particle. This is taken at 250x, and on this part, if you see this zoomed particle, you can even identify based on the texture, based on what kind of color it is getting. Based on that, you can easily tell what kind of product it is. So these are a few of the examples. As I can see, the backscattered electrons, they work under the backscattered electron coefficient, and usually the atomic number plays an important role here. If atomic number is higher, then it will have higher brightness. For example, lead is brighter than the aluminum because more electrons are backscattered from lead than aluminum. Okay, just in case of a concrete mixture, calcium oxide is brighter than alite, and alite is brighter than barite or silica from limestone. For example, if you see the previous, I would like to show and say, okay, coming to this part, from this, what I'm able to understand here is, at least everybody can guess, right? This is one of the pore, or as you can see, this is at lower magnification, 60x zoom, and this is at 130x zoom. At 60x zoom, the voids look very small. If you zoom higher, then you can clearly see these are the voids. The black portions that you are seeing, those are pores, And the whitest portion that you are seeing here, there is whitest portion, here there is whitest portion, and along with some, there are some portions of white. So in image analysis, you can easily quantify them using the grayscale value. The grayscale value of backscattered electron ranges from 0 to 256. Remember, this is just like a black and white photo. Based on the gray value, we are trying to identify the different compounds of hydration in a particular area. This is unreacted cement. The brightest part will be unreacted cement. Next to that, this is the brightest, lesser brighter than this. All these you are able to see, right? Here, 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 here. Those are called as calcium hydroxide. The first is brightest is unreacted cement. The next brightest is lesser brighter than this will be calcium hydroxide. Then comes the hydration particles such as calcium silicate hydrates. See here, these are calcium silicate hydrate, calcium silicate hydrate. Here also some calcium silicate hydrate. And next is little gray ones. These are sand particles, sand particle here, here, here. All these are sand particles. And the final one, darkest ones, they are the pores. Here also you can see this is one of the sand particle, another sand particle. This is one of the void. These brightest parts, they are unreacted cement. Less brighter part, they can be calcium hydroxide. And how do you identify that? With image analysis, you can easily classify. Through our bare eyes, you can make the distinction that whether it is calcium hydroxide or calcium silicate hydrate. If you want to identify the difference between calcium hydroxide and unreacted cement, then you have to go for some image analysis tools. If you feed this image in ImageJ software, then if you threshold the value with different thresholding values, every material, for example, voids from 0 to 32 or 34, if you threshold that value, then only it will show voids. Then higher, every material will have higher thresholding values. If you threshold, then you can easily get the what kind of material present in that image. Okay, so if you have worked on image analysis tool, then what I'm trying to say, you'll easily catch it. Or else just remember, the brightest part will be unreacted cement, next brighter will be calcium hydroxide, then CSHL, then sand particles, then after that it will be pores. So likewise, always ACM is attached with another technique, that is energy dispersive X-ray microanalysis, or in other terms EDX. It is similar to EDS, X-ray microscopy. Previously they used to call it as EDX. Now it is EDS. It is little advanced than EDX. Now whatever we see in nowadays, it is EDS, energy dispersive spectroscope. Okay, what are the uses of this EDS? First thing is, we can see the elemental composition here. What kind of elements are present? How much of silicon is present? How much of calcium is present? How much of magnesium? All that can be analyzed through this EDX. Okay, so I'll show you some of the results that we have got. From that, it will be more clear for you. So liquid nitrogen, this is one of the ACM. These are just components. This is not required. Okay, fine. So EDS analysis, this is one of the typical EDS image. This is the gray, pink color one or purple color one, what you are seeing. This is the area that I have selected, and these are the values that I'm getting. Okay, so that is elements. Which are the elements? Oxygen, magnesium, aluminum, silicon, sulfur, S, Ca, Fe, all the elements, they are available. This is the weight of that material, actual weight in that it shows. But however, it is very much difficult to measure this one properly. That's why we always go for atomic weight, percentage atomic weight, because this doesn't vary depending upon the amount of magnesium or aluminum present in the material. This always remains same. So while going for some ratios, some Ca by Si ratios or Si by Ca ratios, for calculating of those ratios, we always go for atomic percent, not weight percent. Remember that we always go for atomic percent. See here, the silicon content is very high because this one is a sand particle. silicon content is very high, little sulfur, little potassium, calcium is also little bit, some Fe is also there, some carbon is there, oxygen is very much higher. Why oxygen is very higher? Because in the chamber, the little bit of oxygen will be there, even it will detect that also. So this is how we can analyze which compound is predominant. Also, we'll get another spectrum like this. See, the silicon content here is very high. And different components, Fe is available, calcium is available, potassium, all those materials are available. But with respect to the intensity, you can easily identify which compound is higher. But if you want to see the value, then you have to go for atomic percent values. Okay, this is another typical image where you can see the silicon content is somewhat this, calcium content is this, and we usually worry about most of these things, silicon and the calcium, some potassium and aluminum also in some other cases. But in my case, the very important two elements are silicon and calcium for me. This is another typical spectrum you can see of EDS analysis. So now this is all about the background that we have studied. Now let us understand the production and microstructural investigation on RPC. Okay, so these are the materials that I have used. Cement, OPC 53 grade. Also, I have written the IS codes also, which comes under silica fume. It is undensified silica fume, which complies with the IS code of this and ASTM code of this. We have used quartz powder. Size varies from 100 to 45 micrometers. Silica sand, see the range, 150 to 600 micrometers. And this is zone 4 silica sand. Silica sand, if you don't have this fine particle, then you sieve, collect different materials and use only these materials and classified as zone 4. We have used superplasticizer, Master Clinium Sky 8276, which is supplied by BASF. We have used water, that is potable tap water. We have used two kinds of fibers. One is polypropylene fiber and polyester fiber. Some of the studies, what we have done also involved the effect of high temperature. What happens to our reactive powder concrete if we expose them to 1000 degrees Celsius, something like that. So we have studied that also, but I'm not covering that part one here. These are the materials that I've used to produce reactive powder concrete. The next part is there are three experimental programs that we have done. In first phase, it is about the production. Second phase, it is curing conditions. Which curing condition will give me the highest strength that we have explored. And third is RPC at elevated temperature. The phase 3 part is I'm not involving here. We are not discussing here because of time constraint. So we will be concentrating on phase 1 and phase 2. Phase 1 concentrate on production of reactive powder concrete. In the production, there are different parameters or different method which will affect the strength of concrete. The first parameter is effect of mixing method. How do you mix? Which method you use? That is the first parameter which will affect. The second parameter is mixing speed. As you have seen from that video, at what speed you mix, that's also affect our strength. The third parameter is effect of mixing duration. How much time I have to mix? Fourth one is microstructure analysis. Okay, so we have studied the effect of mixing method. Which ingredient should be added first? Water. When should we add water? When should we add superplasticizer? All that is not clear yet in the literature. So we have made an effort to classify or find a perfect method from which you can get the highest possible strength from locally available materials. Okay, so we have classified mixing method, mixing speed, and mixing duration. For all these, we have studied the microstructure. What happens if I use different mixing method, different speed? All that we have studied, and we'll discuss them. So after mixing, once we produce reactive powder concrete, we have to get the highest strength. We have used different curing conditions, different heat curings, so that which combination will give us the highest strength. That also we have studied, so we'll discuss them. This is a 3-stage mixing, and the next one is 4-stage mixing. The first thing, it is dry mix all the ingredients such as cement, silica fume, quartz powder, and sand. In the first stage, we'll mix all the materials. Then in the second stage, we will add half of the required water and half of the dosage of superplasticizer, and we'll mix them once again. In the third step, add the remaining water and half of the superplasticizer dosage, that we are calling it as third stage, and finally we'll get the fresh mix. So this method was already suggested by one of the researcher in China. They are following this three-stage method. Unfortunately, we were not able to get the strength what they were recommending. Even though our material properties were same, all the specific gravities were relatively close, but still their strength was around 300 MPa, but we couldn't get that much amount of strength. We used to get around 160 MPa strength. So we have decided that I should try with some other mixing methods. So we have come up with another mixing method that we call it as I call it as three-stage mixing method. In first stage, we add all the ingredients, dry ingredients, then half of the water, half of the dosage superplasticizer. We'll mix for some time. Then we will add the remaining water and we'll mix for some other time. That's how we get the fresh mix. So this is one method. We call that as three-stage mixing method. So next one, we have tried with another mixing method. First, we only mix the cement and silica fume in four-stage mixing method. That is, I'm calling it as first stage, cement and silica fume. Next stage, I'll add 80% of the water and full dosage of superplasticizer. 80% of water and full dosage of plasticizer in second stage. Then I'll add another remaining two ingredients. See here, in first stage, I'm adding only cement and silica fume. These are the ones which will give us the highest rotation effect, or you can call that as the slump value or flow value we are getting from cement and silica fume. That's why we have added all this dosage of superplastic and 80% of water in this second stage itself. In the third stage, we add the remaining two ingredients, that is sand and quartz powder, and we'll mix for some other time. At the fourth stage, we'll add the addition of remaining 20% of water and we'll mix for some 10 to 15 minutes. Then we'll get the fresh mix. So by doing just changing the way we mix the ingredients, there is a lot of change happening in the fresh properties as well as hardened properties. Okay, so what are those? We'll discuss. And also we have tried with the different speed also. As I mentioned before, speed is one of the important parameter. Mixing stages, as I said, 1, 2, 3, 4. 1, 2, 3, 4. There are 4 stages of mixing. 3 stages also we have results, but finally we have finalized 4-stage mixing method because we are getting good strength in 4-stage mixing method. So once we finalized that, we needed to finalize the speed as well as how much duration I should mix. So for speed, we have taken 25 RPM, 50 RPM, 100 RPM, 125 and 150 RPM. And at stage 1, these are the different times that we have selected. All this is based on trial and error. So what we observe in field conditions, depending upon that, we have changed different things, and finally we have arrived at these speeds. Okay, and this is at stage 1, for example, I'll use for 25 RPM maximum speed. At stage 1, I'll mix dry ingredients at 6 to 8 revolutions per minute. At stage 2, after adding the 80% of water and all the superplasters dosage, I'll increase speed little bit to 12 to 16. At stage 3, I'll add another two dry ingredients and I'll increase the speed to 20 RPM. At stage 4, the maximum speed, I'll add all the water and I'll increase it to 25. Same holds good for 50, 100, 125, 150 RPM speeds. Duration also for 10 minutes, 15 minutes, 20, 25, 30. And if you ask me how did I select these timings are available in literature. Different people are using different time. So depending upon the type of material that you use, the duration of mixing may also vary. Okay, so for your material, you have to finalize what is the optimum duration, optimum mixing duration. So that is what I've tried here with these things. Let us understand a few of the results that we have got. So before going to results, let us discuss also the curing regimes. Okay, so how much time I have to use. WC means this is just water curing. This is ATC, means ambient temperature curing. I have kept the samples in humidity chamber where the ambient temperature is maintained 18 to 24. That is the ambient temperature. So ambient temperature are maintained in humidity chamber. One is air curing. In few of the conditions, we don't have actual water to cure the samples. They usually keep them in dry conditions. So we have tested with also air curing without any water or even humidity, also just air curing, keep the samples outside. Another one is hot water curing. We'll keep the cubes after 24 hours remaining from the molds. We'll keep them in hot water up to 80 to 100 degrees Celsius, boiling water. We'll keep them. Then we'll study the what is the effect on the compressive strength or mechanical properties. The last one is hot air curing. Hot air curing is once we have removed the molds from, we get the cubes from the molds, we'll keep them in oven at different temperatures. This we got from one of the literature from China. They said that as you increase the temperature 100 degrees Celsius, 120, 130, 140, at each temperature, the strength of the reactive powder concrete was increasing. So that's why we wanted to try. We wanted to see how the temperature will affect my compressive strength. So these are the durations that I've tried: 1 hour, 3 hours, 6 hours, 9 hours, and 12 hours. At all these parameters, I've tried at different temperature and how they will behave. So after 12 hours, we'll keep the temperatures, or this is another regime that we have studied. Normal water curing up to 28 days we have studied, 1, 3, 7, 28 days. What will be the strength variation? So this is in humidity chamber at 28 days we have studied. All these methods, hot air curing or hot water bath curing, those are used in precast industry. In precast industry, they want very high early strength. So they cannot wait up to 28 days. The maximum curing days will be 7. They are ready to spend more amount of energy here. So that's why for such people, what will be the strength achieved at 100 degree, 150 or 200 degrees Celsius, that we wanted to study. So we have taken these 100, 150 and 200 degrees Celsius hot air curing for reactive powder concrete. There are some combinations also. We have tried combinations of 12-hour hot water curing and hot air curing at 100 degrees Celsius for remaining period for one day, 2 days, 3 days, and 7 days. These are group A, group B, and group B, group C. 12-hour hot water curing plus 150 degrees Celsius, 12-hour hot water curing plus 200 degrees Celsius. These are some different curing regimes that we have selected based on literature. So these are a few different temperatures we have exposed our samples. This I'm not discussing in today's class. As you can see, flow value. As I told you, this we have selected 4-stage mixing and the 3-stage mixing. In 4-stage mixing, there is sequence A, B, C, and D. As you can see, I'm getting the high flow value. Flow value, see, it's mm. I've used flow table to measure the flow value. In 3-stage mixing, the flow is around 185 mm. If I go to 4-stage mixing in sequence A, I have tried with different sequences. As I told you, the final sequence will be sequence B, where I've used all the cement and silica fume in the initial stage. After that, I've mixed it for 1 or 2 minutes. Then I've added all the 80% of the water and 100% of dosage of superplasticizer. Then after 2 to 3 minutes, I've added another 2 ingredients, that is sand and quartz powder. Then after that, finally it is 20% of remaining water. This sequence has given me highest flow value. Okay, so in terms of flow, I have to go for sequence B. But let us understand whether this sequence B is useful in getting the required strength or not. Okay, so as you can see, the compressive strength also we have studied for 3, 7, and 28 days. The same trend we can notice here as we have seen in terms of flow. And flow and compressive strength, they are directly related. If you have high flow, then the compressive strength will be higher. At least in my case, it is directly proportional. For sequence B, I'm getting the highest compressive strength without doing anything. Just it is normal water curing. Normal water curing at 28 days, I'm getting around 130 MPa strength. So this is the microstructure study that I can come up with. We have selected a few of the microstructures, and these are the just two representative images that I've shown to show what is the effect of 3-stage and 4-stage mixing. In 3-stage mixing, as you can see, there are lots of voids and lots of cracks in and around the interfacial transition zones, and the IT set is porous. As you can see, the IT set is porous. Remember, if you want to compare two things, your magnification should be at the same level. So x equals to 200, x equals to 200. These are backscattered electron images. Backscattered electron images. So in 4-stage mixing, this is the B part. In 4-stage mixing, as you can see, this is the sand particle. Here also, this is sand particle. The interfacial transition zone is very much dense compared to 3-stage mixing. Okay, that might be one of the reason for good strength, for achieving good strength or good flow for 4-stage mixing. Compared to the next parameter that I wanted to compare was the speed of mixing, at which speed I'll get the maximum flow value. For 25, the flow value is around 160, 50 it is around nearly 175. For 100 RPM, I'm getting the highest. If I increase more and more speed, the flow value is decreasing. If I increase the speed, the evaporation water was very high for 125 RPM speed and 150 RPM speed. I also have few of the images here. See here, this is 25 RPM, 50 RPM, 100 RPM, 150, and 125 and 150 RPM. This is the side of the drum that we are talking about. 25 RPM, the material is adhering to it. 50 RPM, it is coming down. 100 RPM, see, it is almost flowable. Okay, as I increase the speed, there is a lot of clumsiness and water was getting evaporated. Because of that, the flow value was decreasing. The same case we have noticed for 150 RPM. So what is the effect of this on our compressive strength? Let us see. So 25 RPM, it is very slow. We have seen even some of the lumps formation happening at 25 RPM, which is not at all suitable. So minimum recommended speed I'm suggesting is 50 RPM. Go for 50 to 100 RPM. Okay, the 50 RPM purple one, it is here, somewhere here. See the strength development 3, 7, and 28 days. At 28 days, the green color is the highest compressive strength. Where is the green color? This is 100 RPM. So at 100 RPM, I'm getting the highest flow also, and also highest compressive strength. So based on this, I have finalized my rotation speed should be 100 RPM and 4-stage and 100 RPM. If you see some of the microstructural analysis, because of high speed mixing at 25 RPM, there are some entrapped air voids within the concrete. In 50 RPM or 100 RPMs, you could see the dense microstructure. As I've used the fractured material, see, I've used secondary electron images. Wherever it is required to use backscattered electrons, I've used backscattered electrons. And for surface analysis, I've used secondary electron images. If you see the flow value and mixing duration, after the speed, how much duration I should mix, that is also one of the important parameter. So I've tried with 10, 15, 20, 25, 30. In literature, people have suggested up to 30, from 5 minutes to up to 30 minutes. 5 minutes, our mix was not proper, so that's why I have neglected. So I've started with 10 minutes, 15 minutes, 20, 25, and 30 minutes. At 15 minutes, I'm getting the high flow value also here, little higher than 10 minutes. So once I increase the time, the flow value was decreasing because of evaporation of water. As you can see, for 10 to 15 minutes, the mix was very good, cohesive. So the same thing we can observe in our compressive strength also. 15 minutes, the strength is higher. So for this, we have conducted even microstructural study also. This is the A part is 15 minutes mixing. Dense microstructure you can observe. This is not just the only one microstructure image. We have a lot of microstructure images. So even if you want to publish papers, they will usually ask you on what basis you are concluding that on one point or one image. Are you concluding this? No, we are not concluding on the basis of only one image. There are lots of images. We have used a technique of student t distribution factor. It will give us the statistical value, how many images that are required to conclude these results. So we have used student t distribution factor, and we have concluded that 15 minutes, this is the image. I'm just showing you one of the typical image that we have got. So for 30 minutes, if you go for this, you can see a lot of voids. Lot of voids can be observed, and these are all secondary electron images. Okay, fine. So next one is compressive strength, normal water curing. Once the mixing method is done, the second thing is how I can achieve early strength with respect to different combinations of curing that we have discussed. One is normal water curing, ambient air curing, or accelerated curing, hot air curing, and hot water bath curing. In all these, the hot water bath curing was showing the highest compressive strength. See, the compressive strength achieved here is around 120 MPa for hot water curing, just hot water bath curing. So we were not satisfied with the results at all. That's why this is one more kind of same graph. As you can see, this is similar thing. I've shown that in a different way. 28 days at, this is the 28 day strength for normal water curing. 28 days strength comes out to be around 100 MPa. For hot air curing and ambient air curing, it is under nearly 100 MPa strength. But if you go for different curing regimes, for example, hot air curing, hot water bath curing, accelerated curing, you can achieve more than 28 days strength of water curing by using different curing regimes. That is hot water bath curing. The hot water bath curing is showing nearly around 110 MPa strength, even at just 7 days curing. 7 days curing, you can achieve 28 days normal water curing if you use hot water bath curing at 80 to 100 degrees Celsius. These are a few of the microstructural images. We wanted to know why the strength is increasing as I increase the temperature. Okay, so as you can see, these are needle-shaped ettringites. A is 12-hour duration. This one is water cured sample for 12 hours of duration. Ettringite, you can observe the magnification is 1500. All the magnifications are at the same, because if you want to compare few things, magnification should be at the same level. Ettringites we can observe for water bath curing. B is accelerated curing. Some crystal CSH we can observe, and C is for hot air curing. Unhydrated particles we can observe, and for D, hot water bath curing. Dense microstructure is available for hot water bath curing. As you can see, compared to all these, water, accelerated curing, hot air curing, the hot water bath curing is giving me a dense microstructure. From this, we can conclude that if you want to get high early strength, then you have to go for hot water bath curing. Even we have studied the combination also. So this is the different compressive strength, hot air curing and hot water bath curing. Hot air curing also, some people have suggested that hot air curing at 100 degree, 150 and 200 degrees Celsius. We wanted to compare with one of the Chinese author. He has said that as you increase the temperature, you can increase the compressive strength. Same thing we also have noticed. As you increase the temperature, normal water curing, ambient curing, this is hot water curing at 100 degrees Celsius, hot air curing at 150 degrees Celsius, hot air curing at 200 degrees Celsius. As you increase the temperature, the compressive strength is increasing up to 7 days. Even in 7 days only, we are able to achieve nearly 150 MPa strength if you increase the temperature to 200 degrees Celsius. If I go beyond 200 degrees Celsius, some of the people might ask, why did you stop at 200 degrees Celsius? If I go beyond 200 degrees Celsius, we were noticing some reduction in compressive strength because the calcium hydroxide was getting decomposed. From literature we came to know, and we have stopped ourselves at 200 degrees Celsius only. As you can see, even 28 days strength can be achieved with 7 days only with hot air curing at 200 degrees Celsius. What is hot air curing? We have kept the samples in oven itself. Oven which has the capacity up to 250 degrees Celsius, we are kept in that. So you can achieve the strength in just 7 days, nearly 150 MPa strength. So for that, we have done some microstructure studies also. These are tobermoids, xenolites, and secondary particles of tobermoid. These are the families of CSHL. As you can see, at 200x to 2000x, sorry, 2000x, we can find a needle-sized tobermoids. These are starting. They are started converting to CSHL, right? At 150 degrees Celsius, as you can see, 3 days 150 degrees, 7 days 100 degrees Celsius, needle-like structures. Then 3 days 150 degrees Celsius, thick fibrous tobermoid is observed. Then C part, C is 7 days at 150 degrees Celsius. This is 3 days and 7 days. The size of these needle-like fibrous tobermoid are increasing as you increase the temperature and curing duration. Okay, and at 7 days, 3 days 200 degrees Celsius, you can see plate-shaped xenolite particles. These xenolite particles are also the family members of CSHL. As temperature increasing and days are increasing, they are trying to form plate-like structures. From needle, they're trying to convert into plate-like structures. Okay, so these will contribute to the early strength development of our concrete. That is why at 200 degrees Celsius, we are getting highest strength. So this we have confirmed from our microstructure study. So also we have done some EDS analysis also on the same part. As you can see, the SI by CA ratios. SI by CA ratios for 100 degree samples, 7 days. The SI by CA ratio is 1.05. At 150 degrees, SI by CA ratio is this much. And at 200 degrees Celsius, the SI ratio is 2.04. What is happening here? The silicon content, CSHL, calcium silicate hydrate, the silica is getting improved as we increase the temperature. So that is the reason why we are getting highest compressive strength at 200 degrees Celsius. Okay, that we have confirmed with even energy dispersive spectroscopy analysis or EDS analysis. So same thing, we have also tried with the different combination. 12 hours of hot water bath curing and hot air curing at 200 degrees Celsius is giving me the maximum strength. We have achieved up to 180 MPa strength. In our case, I could achieve around 180 MPa with this combination. That to remember, this strength we are getting only at 7 days, because in site we need our maximum strength within 7 days. Okay, when I kept this same samples up to 28 days, they have crossed around 210 MPa strength. Same thing I've represented in a different way. This is just for hot water curing. If you go for hot water curing at 12 hours plus hot air curing, remaining 7 days, hot air curing at 200 degrees Celsius, you can achieve highest compressive strength within 7 days. So these are some of the SEM images where you can see zonolite secondary particles and zonolite particles. These are just family members of CSHL. They are converting into different forms. Initially, they are unreacted cement grains. Then B is hot air curing group A, that is 150 degrees Celsius. They are converting into secondary zonolite particles, and phases of these are converting into these shapes at the end. And ultimately, once they convert everything, they become dense microstructure. So people started asking us, how do you say that these zonolites and are available in the material? We have got one of the comment from one of the CBM reviewer. As you can see, we have the literature support for these, but how do you confirm whether this material is available? Zonolite or secondary zonolite particles are available in your mix. For that, we have gone for even XRD analysis. So in XRD analysis, we could see these peaks. Okay, so in XRD analysis, if you people have done, I'm running out of time. That's why trying to wind up as early as possible. These peaks, these are at different 2 theta values. At 2 theta values, JCPDS software JCPDS software, we have compared this data with at what angle what compounds will form. So from this, we have concluded that the first one, as you can see, those are CSHL. Second one is tobermorites, and third one is calcium silicate hydride. These tobermorites are family members of CSHL. Even they are contributing to early compressive strength. That is what we wanted to try with even XRD analysis. So one more images, and here you can see zonolite secondary particles and tobermorites. So what are my conclusions or observations from the present study? If you want to produce a reactive powder concrete, the first thing you have to fix the materials. You have to have high amount of cement. Second is silica fume, quartz powder, silica sand, superplasticizer, and very low water cement ratio. So then comes, how do you mix it? So my suggestion is you start mixing with phase in 4 stages. First is you only dry mix cement and silica fume for 2 to 3 minutes. In second phase, add 80% of water and full dosage of superplasticizers, then mix for 3 to 4 minutes. After that, in third stage, you add silica sand and quartz, then add remaining water and mix it. So that's why you could get high compressive strength as early as possible. Then time also we have mentioned. If you see our papers, you can get the details of it. One thing is that, so to confirm all the hypotheses that we are making, we have gone for our microstructure investigation. And if you're few of the reviewers are recommended that microstructure investigation is subjective, that's why we also went for even XRD analysis. Okay, so if XRD is also not sufficient, then we wanted to go for FTR analysis, Raman spectroscopy. There are so many other methods to confirm what is exactly happening or what kind of hydration products that we are getting. Okay, so in this presentation, I want you to take only 2 things from this presentation. There is a ultra high performance concrete, which we are able to produce in India with the locally available materials, that is reactive powder concrete. Anybody can produce even reactive powder concrete. With little Hobart mixers also it is possible. In my MTech, I've used only Hobart mixer for producing reactive powder concrete. And without hot water curing at 28 days, I could achieve 180 MPa of strength at 28 days. Okay, so one thing is that you can produce reactive powder concrete. So if you want to suggest or fine tune your research, you have to go for microstructure analysis with different methods. Okay, one method is SEM, ETS. Even you can go for XRT, FTIR, Raman spectroscopy. There are different methods. From that, you can confirm what exactly happening in cement. That is, study the cement chemistry with microstructure analysis. These are the different references that I have used. And thank you. That's all from my side. I took a little bit of your time because the presentation has started a little bit late. So I'm open for your questions if you have any.
Thank you, sir.
Yes, ma'am. If you have any doubts, ma'am, you can ask. Some people might put that in chat box. I'm not able to see the chat box right now. So if I have any questions, I'm happy to answer.
Participants can ask the question.
Hello.
Yes, sir.
Sir, in case of what you shown that images, actually they from Australia, Japan, Canada, like developed countries.
Yes, sir.
But in case of India, where we are standing as an experiment on case of RPC, or where we are going to applying, because so many works are going in next 4 or 5 years on infrastructure. That's
yes, sir. Yes, sir. That's a really nice question, sir. Jadhav, right? I guess. Jadhav,
yes,
sir, that is a really nice question. One thing, still we are at the experimental stage in India. There are hardly few universities who are working on this. NIT Surat Kali was one of the premier institution. They have started working on this. Now IIT Madras, IIT Delhi, IIT Bombay, those people are pioneers. Also, if you want, in IIT Bombay, they are starting this big infrastructure projects with using reactive powder concrete. But in India, as of now, it is in research stage. All those 800 or 200 to 800 MPa strength concrete, if you want to produce, all of them are patented right now. They have patented in China, France. If we cannot use the same material, same mix design, if you want to use, then we have to pay them. That would be a costly affair. That's why we are researching with locally available materials what kind of best reactive powder concrete we can produce. We are working on it, and with more amount of research, even we can produce. I'm sure within 2 or 3 years you can see the structures, right? Highway projects, people are started using them because the slab thickness will be very less compared to the normal RCC ones, and it is also more durable. It's coming, sir. Within 2 to 3 years, you can see reactive powder concrete constructions. L&T will be the first one because as of I know, I have got one of the mixed design for reactive powder concrete that is from L&T. That was for minor work, not of bridge or anything. I have done the mixed design for that because they have come to COAP. They have approached me. I have done it. That means some amount of development is happening in the field of reactive powder concrete. Within 2 to 3 years, you can see some beautiful structures out of this.
And sir, you are minimizing or directly neglecting the passive steel parts.
Yes, sir.
So what are remaining for designers?
Sir, in some of the cases, it's very congested. If you see the self-compacting concrete, if the reinforcement is too heavy, then even we cannot use self-compacting concrete. In such cases also, you can use reactive powder concrete if it is very congested, because we are not using any silica coarse aggregates here. But however, the objective here is to remove that entire reinforcement, because that is being taken care by our steel fibers or another kind of fibers.
So that means if you compare to this RPC with the normal one, general operating.
Oh yes, you can compare.
That means total structure cost can be we can reduce also.
Oh yes, you can reduce cross sections of all the structures considerably.
Yes, thank you, sir.
Sure, sir.
For your answer.
Are there any other questions from participants?
Participants can ask the question.
अगर कोई पूछ नहीं रहा है तो that means that was monotonous, boring. As this was a research part, so I had to cover a lot of things in very short period of time. That's why I focused all the things on PPT itself. So I'll share this PPT with you guys. You can watch, and if you have any other problems, you have my contact details here, or else I'll give my contact details to the organizers. You can contact me anytime.
Yes, sir. You can give your email address also, so that if participants have any questions, they can mail you.
Yes. I'll share my email address. That is skg.civil. I'll put that in chat box also if you guys want.
Okay, sir.
I'll do that right now. Where do I type? So that's my email address. So if you directly want to contact me, so this is my contact number. You can contact me anytime.
Yes, sir.
95385609. Yes. We can even have collaborative sessions also if you have MTech students working in your department. We have equipments in our civil engineering department, COAP. Send your students to us. We can have a collaborative work. A lot of things can be studied. Even COAP has its own SEM equipment, scanning electron microscope equipment. We can literally work on that. So if you are interested in collaborative works, please contact me. Yes, and organizers, really thank you for providing me an opportunity to speak and eat your head at least for 1.5 hours. Thank you for the opportunity.
Yes, sir. So thank you, sir, for conducting such an informative session on reactive powder concrete production and microstructural investigation.